let's talk about work energy experiment. I would like to take a few minutes and review the work energy theorem. The work energy theorem is very simple. It states like so, that if you add all the work done by all the forces, so let's say we have few forces, work done by force number 1 plus work done by force number 2 by force number 3, and so on and so forth. If you add them up, that should be equal to change of kinetic energy. All right, delta K, which is K final minus K initial. On the left-hand side of the equal sign, instead of showing W1 plus W2 plus W3 and so on, we can show sigma Wi for I going from 1 to n, meaning that let's say that you have 3 forces. So in this case, n would be 3. That would be I for I equals 1, I equals 2, and I equals 3. All right. But this is a general form that we use to show what we have on the left-hand side of the equal sign. Should be equal to delta K, change of kinetic energy, which is, again, K final minus K initial. Okay? So we wanted to test this. If we want to test this, all right, we have a very easy setup. What we have a air track. The air track has a tiny hole on its tiny holes on its surface. Air is coming out of those holes, and it will reduce the friction between the glider. In this case, I'm showing it with a box here. All right, so it's reducing the friction in this surface area between the glider and the air track. And for us, it's a slightly tilted, so we tilt the air track, and so therefore we have a small angle here, usually a few degrees, something between like 1 to like 5 degrees. All right, we do that by lifting one side of the air track up with some height h. Okay, so in our actual experiment, this height h is given. It's a height of a wooden block. So we're holding up the glider. This is the glider up here. So there are tiny holes here in the surface. Air is coming out of them, and therefore this glider can freely, without any friction, slides down all the way to here. So initially, the glider is located at point 1, which is all the way up there. All right? You start the time from 0. You let the glider go from point 1. We're not pushing it, so therefore it's being released from rest. Initial velocity is 0 at point 1. Okay? And then down here at point 2, all the way at the bottom, we have a photo gate. What photo gate does is that anything that passed through the photo gate, it'll give us the velocity. So we know the final velocity. The final velocity is known. Okay? It is coming from a photo gate. Photo gate is connected to the laptop, so we can understand what the final velocity is. All right? So, very easy setup. Initially, we'll let the glider to glide down without any force. So initial kinetic energy, this initial kinetic energy is 0. Remember, kinetic energy was half mv squared. All right? Initial kinetic energy, half mvi squared. So if there's no vi, then there's no initial kinetic energy. At final point, at this point, when it passed through the photo gate, we already know the velocity because the computer is giving us the velocity using a photo gate. Okay, so that is no. So in other words, we know the change of kinetic energy. Change of kinetic energy, again, initial is 0. This is known because we can measure it. It's half m, mass of a glider, which we can measure, final velocity, which the photo gate is giving us. So this right-hand side of the equation, we already know what it is. The left-hand side of the equation, work done by all the forces. Now, how many forces do we have here? If I have a inclined surface and there's a glider on top of it, there's a box on top of that. How many forces do I have? Obviously, there's a force of friction. We're not considering the force of friction here because we think that it's negligible. The only force that is acting on the, so it's actually a force of gravity, mg, and there's a normal force, normal to the surface. Surface is inclined, surface is tilted, so my normal force is like that, right? Normal force doesn't do any work because it always is normal. It is always with an angle of 90 degrees. So work done by normal force is normal force times displacement times cosine of the angle between displacement and the normal force, which is 90 degrees. In this case, cosine of 90 is 0. So the work done by normal force is 0. In other words, this normal force does not work at all. Doesn't change anything for us. Doesn't change any energy of the box. The work done, okay, the only force that's actually doing any work is gravity. Gravity, mg, is doing all the work for us. All right, so on the left-hand side of this equation, right-hand side, we already know what it is. Initial is 0. All right, final is known, half mv final squared, half times mass times velocity is squared. Left-hand side, this part, we have one work done by normal force, which is 0, so we're not considering that, and a work done by mg, force of gravity. All right, that's F d cosine of the angle between them, cosine of alpha in this case. All right, so that is alpha. By the way, for the lab, this alpha should be actually pretty big. It should be like 80 something, 80, 85, 86, 87. I've seen it 88 in the lab. So therefore, this theta is a small angle. It's very small. All right. So here, FD cosine theta, work done by mg, force, which is mg, times displacement, times the cosine of the angle between force and displacement. This angle, which we call it alpha. By the way, it's easy to find it, and you can find it in the lab. Okay. This should be somewhere like 87, 86, 88, something like that. Okay. So cosine of alpha. If you continue with mathematics and using trigonometry, this will lead to mgh. Okay, this d cosine alpha, this d cosine alpha, this displacement here, this d times cosine of this angle, this will be equal to h. All right, so this is h. H is the height that we have here. This is h, all right? And the height is given to us. So on the left-hand side, I have mgh. On the right-hand side, I have k final minus k initial, but we know k initial is 0. And k final is half mass times final velocity squared. Okay? So the whole purpose of the lab is this. What we have on the left-hand side, mass times gravity times h. And what we have on the right-hand side, half times mass times final velocity. Are they equal to each other? In other words, what I'm interested in this lab is to see if mgh on the left-hand side is equal to half mv final squared. Are they equal? By the way, we can cancel out m. So in the lab, you would actually do it with the mass of a cart, and then you would add 100 grams of mass to it, and then you would add another 100 grams, so 200 grams for the third trial. But the thing is, when you look at the formulas, mass on the left-hand side and mass on the right-hand side, they cancel out. So your result is independent of the mass of a cart. Doesn't matter if it's mass plus 100 grams, or if it's mass plus 200 grams, or if it's mass from 500 grams. It doesn't matter, because mass from the left-hand side and the right-hand side can cancel out easily. All right? So what you wanted to do to test in the lab is whether G times H, gravitational constant times height, equals half V final squared. V final is the one that your computer is giving you, or the computer in the lab is giving us, using the photo gate, and H is the height of a block. So that is the lab. The next step will show you what we have set up in the lab, and we'll go from there. First, let's measure the mass of a glider. In this case, I am reading 186.9. But we'll provide you with the exact value for the mass of the glider in the lab data. One side of the air track is lifted upward using a wooden block. The glider glides down from one end to the other end. Here is the blower, which blows air from those tiny holes. As soon as the glider passes through the photo gate will show us the velocity, because the flag on the glider momentarily will block the laser in the photo gate. So we're gonna start from point 1, letting the glider glide down all the way passing through the photo gate. For the second trial, we're going to add 100 grams and redo the experiment again, letting the glider to glide down, passing through the photo gate. The third time we're doing it, we will add another 100 grams. So it's mass of a glider plus 200 grams now. Releasing it from rest from point 1, it'll go through a photo gate. The photo gate will show us the velocity. We need to measure the distance using a meter stick, and we can measure the height of a block using a meter stick as well, which is the H in our calculations.